Why is it coming?
All right, well, first of all, shut up. First of all, everybody, I assume, is doing your research for your paper.
Of course.
Well underway. Done. Is it really?
7,527 bits.
All right, so shut up. All right, so remind me, what's a lexical analyzer? What's the purpose of it? Go ahead, Baker.
Writes the input stream into the tokens. And if it takes it for identifiers, it records what address they're at, and for operators, it generally has an equivalent abstract symbol. It looks like that operator.
Okay, why do we need that? Like, what advantage does it give us? This kind of is a segue into what we're going to talk about today, but generally speaking, if you were to kind of summarize what we have as a final product after we come out of the lexical analyzer, what are we looking at? Well, we definitely have we definitely have lookup tables. That's part of the result. Okay, parse stream of what? What is it? Would you agree that when we have our initial source code, it's very random because we have so many different variable names and things like that? After the lexical analyzer, we have essentially a collection of tokens, but these tokens fit into individualized categories. We don't have 4 million different variable names. Now they're all linked identifiers, right? And we can treat every identifier the same. And then, as Joey pointed out, we can go look up the actual identifier, the actual variable name on some table when and if we ever need it. Correct? Okay, so really what it's done is it's dumbed down our source code into something more generic. Okay, that kind of makes sense? It took all the personality out of it. Or have I found with what I have found with computer science students is some of the profanity
is removed.
Yeah, you get profanity in comments. Sometimes you get variable names. When they don't know what they're doing, sometimes they actually just make up syntax that is. That is a valid operator. Wait, where's Diego? Go, Diego, go.
He went. He went nowhere. He go.
Was Dora on campus?
It's a condom map.
Is it Diego that has the monkey friend, or is that Dora?
I'm not really sure, sir.
Great question.
I'm not familiar with this.
Yeah, it's probably all of literature.
Okay. First of all, who's lying?
It's Dora.
And it doesn't have to be that you like watching the show. It just means you have a niece or nephew or something.
He doesn't.
Yeah, for
Older.
Saturday morning, a common show in my house was My Friend Rabbit. There's a kid show called My Friend Rabbit where they do a hop think. That's how the kids they learn to like solve problems. They hop around while they're solving problems, I guess. My wife would just claim that, oh no, I just watched that channel. That's what comes on.
Really did.
I see her sitting there watching that show. She said, that was a good show. But yeah, I mean, so I span the age groups with my nieces and nephews. So it's like you got Barney. Barney's a has-been now, right?
He's extinct.
I don't think anybody likes Barney anymore. Then you had Baby Bop.
I think it's all
It's Elmo?
What was that one crazy kids show?
All right. So, anyways, we have our output of our lexical analyzer, which your book calls a token stream. Okay? So, generic syntax. Okay, so then we have something called a syntax analyzer. And the output of that is a syntax tree. Well, let's look at what this guy does. So as a reminder, remember last time we were looking at something like this. Position is equal to initial plus rate times 60. And that got rewritten to this as our token stream. Okay? Notice that each token is inside of less than, greater than signs. So that's how we're establishing tokens. That make sense? So this is just a collection of tokens. We can think about it as being all on one line. We can think about them as being on separate lines, but we're ignoring white space between tokens, and each of these tokens means something. Okay? So we can almost think about this as almost like HTML to a certain, from a parsing perspective. Okay. So now, here's our kind of the punchline. So lexical analyzer, here's the output. Then we go into the syntax analyzer, and look what the syntax analyzer does. It builds a source tree. So this is a tree data structure. And notice that every place that we have an identifier, those become leaf nodes. Every place that we have an operator, they become root nodes. So far left, ID1 equals ID2 plus ID3 times 60. So if we were to build an algorithm to produce that tree, how would we go through this token stream and actually produce this? What would that algorithm look like? Go ahead.
I hate to say it, but it'd probably be recursive.
Could be. Doesn't have to be. Pop quiz. Not a collected quiz, but a let's see if you've learned anything quiz. Any program any recursive program could also be written using what and a what?
Pencil and paper.
Okay. A loop and what?
Computer.
Any program we could write recursively, we could also write iteratively using a loop and a...
Counter. Case. Switch. What are you fishing for, sir?
I'm fishing for the right answer. There's only one right answer. I'll give you a hint. You want a hint?
Yeah. Yes.
Should I let Ian answer first?
Is that like Happy Puke?
No. It might be internal bleeding puke, actually. Some of the positions I got into last night.
What?
All right. For the recording, there were some statements made before the recording started. I did a yoga class last night. I always use
new techniques.
Actually, it was here's a funny thing from the yoga class tonight. So the course is called Yoga for Golfers. So they're offering it by a country club, and so they try to put everything into golf terms in terms of like what muscles you're working and how that's going to translate into your swing. And then if you've been in any sort of workout class, they have kind of like the normal way of doing it, then the more advanced way of doing things. So she would call the normal way the par way of doing things, and the more advanced way the birdie way of doing things, like a birdie in golf versus a par in golf. Okay, so we're doing this one thing. We're doing this one twist thing, and my gut was like way too much in the way. Okay, so I raised my hand. I'm like, I'm going to need the triple bogey version of this. True quote from class.
Beautiful. So what is the other word? Loop.
Oh no! Okay, I was going to give you a hint.
Oh, yeah.
I was going to give you a hint before you guys painted me into a corner. I mean, geez, I had to come up with that yoga excuse on the time. All right, so how does recursion actually work? Well, no, that's what recursion is. How is we wrote recursion last semester. How does recursion actually work? How is it implemented?
Stops after the loop and runs.
I almost thought you had the right answer until you started saying stupid stuff.
So it'll finish whatever's on the top call and then get to the next call with that output and go through down to the bottom of the stack.
Stack.
He said that like 2 minutes ago.
Yeah.
Way after he said other wrong things, correct? I never heard him say stack. Yeah. Any recursive solution could be rewritten iteratively using a loop and a stack. Why is that? Well, because recursion is implemented in terms of a stack. So you're just not doing the built-in recursion. Instead, you're writing your own, I don't want to use recursion. All right, so back to my question. If I have a token stream that looks like this, is this going to highlight right? No. This guy. If I have a token stream, I can't even do a straight line. That arm's not working. I'll have to use my one with tremors. So if I have a token stream that looks like this, what algorithm could I use to produce a syntax tree like this? So we need to make it consistent, especially if we're going to end up writing it. So here, let me can I copy this? All right, so we have ID 1 equals ID 2 plus equals ID 2 plus ID 3 times 60. All right, so we have this token stream. How do I turn this token stream into a syntax tree? When we hear the word stream, when we read this, we're probably reading it in one token at a time. So the first thing we're going to get is this first token. So when I get this first token, where do I put it? Well, right now, first of all, the end result we're going to have is actually a tree, correct? So right off the bat, if I don't have a tree, I need to make a tree, correct? All right, and what's the definition of a tree? Does it have to have one child? No. Minimum definition of a tree is a root node, correct? All right, so we're going to create a brand new tree, and we're going to throw our root node in there, ID 1. Man, I hate Wednesdays. No, I like this class. I just want it to end after this class. Unless there's Chicago people in tonight's class, then I might change my... Oh, no, I'm all about that. Come and put your orders. Anybody who lives on campus, I'll let you know. If we have Chicago people, we can get our Portillo orders in. Text me somewhere around like 7 or 8. I'll be in the middle of class. Just in case I've forgotten to ask, I can then pull the class.
Stop recording.
Give a pop quiz in the middle of class. Who's from Chicago? Are you willing to bring Portillos for the rest of the class if we pay for it for a better grade? That's
Especially
that's all. Actually, I just recorded that. So haha, joking. Ha. All right. So I just read in the very first token, created a new tree with this guy as the root node. Okay. Now, it didn't matter what that token was, at least for our perspective right now, right? We have one token, we didn't have a tree, we created a tree, put the token in the tree. Okay. So, all right, read in my next token. This guy's an operator, right? So let's kind of just, pretend like we somehow can detect operators. We'll have to figure out what that means later. But, we read it in. This guy is not an identifier. Since he's not an identifier, he is something else. Okay? So with the exception of our 60 over here, we're going to say the something else's are operators. So we read in a something else. How do I add this guy to the tree? So we got to go back to our data structure class and think about how trees worked. The trees we looked at, specifically binary trees, we always put numbers into them, right? And if it was less than or equal to the root node, it went to the left. If it was greater than the root node, it went to the right. Correct? Well, that's not going to really fly in this case. So how do we add this guy? Well, we've already seen the result. The result was that the equal sign was at the top of the tree, correct? Okay, so clearly we need to create a new node and set the current tree's head, current tree's root node, equal to the child, the left child of our new root node. That make sense? So far, so good. We're just trying to stumble upon a pattern. Okay. Then, we read in another identifier. How do we know that this identifier goes to the right child of the root node? Because we already have a left child. So we're going to create. So there's our ID2. All right. Now we read in our next. The plus sign. Well, where do operators go? Operators, as far as we've seen so far, become the root of their own subtree, correct? Because isn't it true that a tree is a collection of subtrees? Because Coleslaw told us that a tree can be just a node, single root node, right? Which means that this particular tree, we have a root node with two trees as children, because each of these trees is a single node. Correct? Okay, so we know that an operator becomes the root node of a subtree. Well, the first root node we run into already has an operator in it. Why don't we go to the left? Go ahead.
Because there's already another mod token there. There's already another mod value pair.
An identifier.
Yes.
We already have a value there. Something that's a non-operator, non-other. Okay? So we're going to go to the right. But we have an identifier there too. So the guy we're trying to add is this guy. So we know we can't add it as the root here because we already have an operator as the root. So we're going to default. Let me ask you this. Could we have ever had an operator as the root here and had nothing as the left operator? The left node, rather?
Why not?
Well, let's think about syntax. Typically, we say A plus B, right? So in a language like that, would it ever make sense for us to have an operator at the top level with nothing as a left child?
Like plus ID or something.
Could be. Yeah.
Yeah, like the exception of that is like the difference between L values and R values. Yes, you have to have a single identifier as an L value. You can have, another expression as an R value.
Okay, so you're saying that we treat these as L values and these as R values, and all L values must be identifiers. And all R values can be either identifiers or operators. Okay?
Well, I guess our value being anything to the right of an operator.
Sure. I'm okay with that assumption for right now. So let's operate off that. So we have our plus sign. We know we can't put it at our top root because we already have an operator there. So we're going to default to the right of it because that's the only place, according to your assumption, that's the only place that operators could exist in the R value side of things, right? L values can only be identifiers. So we're going to go to the right. We see this right node is a operator. I'm sorry, is a non-operator. Therefore, we want to insert this guy here and make this guy become his left child. Make sense? All right. Then we read in the ID3. Okay, should not be a root node. Is not going to go to the left because we already have a left node. That is an identifier, right? So we go to the right. We have a root node. Can we go to the left with it? Well, legally we could, but there's already a identifier to the left. So we'll default to the right where there's nothing and we'll add him. Right? Okay. Then we have our multiplication. Okay. Well, we already have an operator at the first root, fail to the right. Already have an operator at the next root, fail to the right. Don't have an operator here, so what are we going to do? Drop the operator in. Bring this guy as the left node. We have our 60. Okay, well, let's start up here. Okay, 60 is not an operator, so it can go left or right, correct? Well, can't go to the left because there's something already there, so we'll fail to the right. Can't go left because there's already something there, fail to the right. Can't go left because there's already something there, fail to the right, and we'll place it there. We see we have identifier equals plus ID2 times ID3, 60. I think we created that tree, correct? Okay, so we think maybe we have an algorithm that to go from a token stream to a tree. We'll experiment with it, but seems like we're onto something there. Okay. On this very simple language that is made up of operators, literals, and identifiers. Correct? And this is a very simplified language where we have equal sign, plus sign, multiplication sign. We can assume there's probably a division sign as well. Then we have literals, hard-coded values, and then we have variable names, our identifiers. All right. What does the semantic analyzer do? Let's look at this section on syntax analysis first. So second phase of the compiler is syntax analysis or parsing. Oh, we like parsing. The parser uses the first component of the tokens produced by the lexical analyzer to create a tree-like intermediate representation. Okay? So far, so good, right? Our algorithm was on par with that. Didn't have a tree, made a tree. Okay? That depicts the grammatical structure of the token stream. A typical representation is a syntax tree in which each interior node represents an operation, and the children of the node represent the arguments of the operation. A syntax tree for the token stream is shown below, blah, blah, blah. So there's our left child, right child thing, left value or R value thing. Right. I think according to that, we're fine. All right, so the next step, semantic analysis. Semantic Analyzer uses the syntax tree and the information in the symbol table, that's the table we created at the very beginning, to check the source program for semantic consistency with the language definition. It also gathers type information and saves it in either the syntax tree or the symbol table for subsequent use during intermediate code generation. An important part of the semantic analysis is type checking, where the compiler checks that each operator has matching operands. That is, the left and right value are appropriate values for the operation that we're trying to do. For example, many programming languages require an array index to be an integer. The compiler must report an error if a floating point number is used to index an array, like array at bucket 1.3 or something like that. Okay. So if we look at the output of the semantic analyzer versus the syntax analyzer, it seems like all it has done is strip away the token portion from all the operators and added a function call for the 60. Convert an int to a float. Probably making the assumption that the multiplication operator must operate on floats or something like that in this particular language. You can look down below and see what it says. Okay, so why has it stripped away the tokens? What does semantic mean? It's a funny way to ask the question, right? What does semantic mean? Semantic means. What is the meaning of something? So we're going through and we're analyzing our tree to bring some additional meaning to what we're actually trying to accomplish. Okay? So at this level, we've gone from tokens to splitting our tokens on operators and tokens. Ultimately, we've kept all of our operators, kept all of our tokens, but we've given some semantic meaning to our literal here by saying this needs to pass through int to float in order to become the value we need it to become. Then we have intermediate code generator, which is going to take our semantic analyzer, this guy, and we've created some hard-coded variables. Think of these like your registers on your CPU. So they've created this thing called T1. T1 is just going to hold the float version of 60. So first of all, notice that we're starting at the bottom of the tree. Then we go to T2. T2 is equal to ID3 times T1. T3 is equal to ID2 plus T2. ID1 equals T3. So we walked our tree from bottom up. Now, an interesting thing here to see about our trees is notice that our tree is unbalanced. When we learned about trees in the data structures course, we talked about balancing trees, where if one side of the tree became deeper than the other side of the tree, searching it became inefficient. Correct? Well, we don't want to start rebalancing this tree because then we break the semantics. We break the meaning of our code. Correct? So by definition, a syntax tree tends to be write heavy. Does that make sense? Okay, so we get our intermediate code generation. So if we follow these steps, we can get a correct answer. Then we go through a code optimizer. Technically, this is correct code, but what can we do? Well, we can say T1 is equal to ID3 times 60.0. That is times the int to float version of 60. So we've cut out we've turned the first two steps into one step. ID1 is equal to ID2 plus T1. So just shorten the code a little bit. Now remember, the idea here is this should be something like, well, they're calling it an intermediate language, so it should be a step towards a low-level language. That makes sense? What we do up here, everything's about massaging our code, our high-level code, into a situation where we can conveniently and accurately and optimally turn it into low-level code. So at the end here, we get the code generator. And the code generator is going to do what we did up here, but for real. This is actual assembly code. So we're going to load into register 2 the value of ID3. Okay, that's this value right here. In order to do this line, we first need to store ID3 somewhere. So we're going to store ID3 into register 2. Then what are we going to do? We're going to multiply floats. What floats are we multiplying? We're multiplying whatever's in register 2, which should be ID3. Actually, is this?
It's like register 2 equals register 2 times 60.
Oh, right. So we're going to multiply register 2 by the literal value 60.0, storing the result back in register 2. So at the end of this line, register 2 is the value of T1 here. Then we're going to load into register 1 the value of ID 2. This guy. Keeping in mind that register 2 holds T1. Then we'll add, storing the result in register 1 plus register 2. And then our final result into ID 1 will be whatever's in register 1. That make sense? So this is the low-level language equivalent of this. So we wrote this high-level code, and it turned it into this. That's what a compiler does. Why did we need all these intermediate steps? Why couldn't we have just gone from this to this?
Computer science is
Problem causing. I like that.
sheer amount of
So why couldn't we have just made that step directly? Could we have? Go ahead.
You say from lexical analyzer to code generator or from syntax analyzer?
Either. I mean, I was really asking from syntax to, why couldn't we go from we have this crap to boom, this is what it actually is? Go ahead.
It's probably wrong, but is it possible that they do so many levels so they can check the work before going through the whole compiler before finishing?
Well, that's actually a very good answer. As part of compiling, we're also checking syntax. And in order to check syntax, we need to, to make sure we're using operators correctly, we need to get down to that level where we can identify an individual operator and also its operands. So we need some of those intermediate steps in order to validate the high-level code that was written. Okay? Why else? Go ahead.
Because the translation is like one to one. 'Cause when it
Oh
gets-
yeah, by definition, a high-level language is going to be a many-to-one relationship. So one line or a one-to-many relationship. So one line of high-level code is going to translate into many lines of assembly code, many lines on the CPU, many instructions on the CPU. That make sense? How many of you have had have either written code in C or C++ or have had any of the iPhone classes? Okay. Remember we used the .h file? We use a header file, right? And what do we do in the header file? Go ahead.
Get the preprocessor information,
Okay, which is what?
basically what functions, what to expect basically when compiling.
Okay, so we are prototyping our functions and variables in there before we actually use them, correct? Okay, why do we have to do that?
I guess if it,
It's a trick question.
I've heard you say if it's a multi-pass compiler, it won't make a difference, but in fact, in single-pass compilers, you had to, or else it would have, if you called something in main that was defined below main,
Mhm. So in this case, we're looking at a fairly simplistic compiler. Old compilers, original compilers, were one-pass compilers. So in a single pass, they went through and created that symbol table and all the lookup tables and things like that that they needed, and also generated code. The problem with that is sometimes you have a chicken or the egg problem that comes up, where you might be calling a function before that function is defined. We see this in Java all the time, right? Most of the time when I write a Java program, we have main at the very top, correct? And we have our functions below main. Yet we're calling those functions from within main. So if we're the compiler walking through that high-level program, and we get to, reverse string function inside main, we haven't defined that function yet. So Java has to just trust us that it'll find it later. Does that make sense? In a multi-pass compiler, that's legit. In a single-pass compiler, like older compilers, like what we're going to look at initially, that won't fly. So you're going to need to prototype those functions. You need to let the compiler know that there will be a reverse string function. You can define it later. You can implement it later. But you need to at least let it know that it will exist and what the header information, what the rules of that guy are, so that during semantic analysis, we can determine whether or not it's being called correctly. Right? We're not actually generating code at that point, so we don't really need all the details. But we do need to know what the inputs are and what the output is so that we can determine whether or not it's being used in a syntactically correct way. That we're not trying to shove a float into an ice cream cone. Make sense? Okay. So there's many reasons for these intermediate steps. A very important one is error checking. Okay? It's probably the most important one. Secondarily, there's a level of convenience. Whether we jump from here to down here directly or not, at some level, we're going to be doing these translations in the middle. It's going to come in the form of scary code, correct? Where this at least takes it through a systematic approach where we start with one thing, turn it into something else, and keep modifying it until we're stuck in a situation where, okay, this format we can now take and do something like this with. Would you agree? Well, here, let me ask this question. In terms of the compiler workflow here, what do you think the hardest part to implement will be? You think code optimizing?
Semantic Analyzer, just by the time you have to put into it.
I mean, I would grade all of them as trivial, but but if one was a little bit less trivial than the others, I would say it's all of it. I would argue that code generation is easily the most difficult. The quality of any compiler is measured by the quality of the code that is generated by it. Now, code optimization certainly plays hand in hand with that. So, I mean, I don't want to belittle that part of it. But realistically, we could probably have an accurate compiler and not even have a code optimizer. Does that make sense? Especially if we're not trying to compete with the modern day C and C++ compilers in terms of performance. If we're good with accuracy, who cares about optimizing? It's like, okay, well, this looks good. Let's just go from here to here. In fact, if you look at it, these two kind of read similarly, don't they? But definitely, the hardest approach is going to be the code generator. As a human being, going from intermediate code generation, this stuff, to this stuff, is far easier than it would be to write a generic algorithm to generate this based on either this or this. So these last three steps are easily where all the heavy lifting are. But, or where the heavy lifting is. These steps up here, relatively speaking, are trivial. This is just string manipulation, right? So, if we were to take something like this, position is equal to initial plus rate times 60, and I wanted to generate this lexical analyzer, we're going to do this next class. How would we write that? What approach would we take? Remember, a couple pages earlier in the book, it talked about this as a character stream, right? So we're reading in our source code one character at a time, building up tokens. I guess we can call them tokens at this point, that's fine. So building up tokens and ignoring white space. That's why we call it a character stream. So how would you go about getting this information? Go ahead.
Looking for operands, equal, plus, and multiply. Because if you're taking out space, otherwise you can parse by space if you add the space in there.
Okay. Well, if you walk through this guy, what is the delimiter of all of this? It's white space, correct? So we have position, followed by white space, followed by equal, followed by white space, followed by initial, followed by white space, so on and so forth. So if we just start reading in one character at a time, ignoring white space until we finally hit something that's not white space, so we can have 4 million spaces before position, then all of a sudden we hit something that's not white space. So we're going to start building up this token. Capture the P, the O, the S, I, T, I, O, N. Then we hit white space. Done. We just read in a token. Now we need to analyze that token, because we need to replace that token that we read in with its functional equivalent. The output with its lexical equivalent. Let's go that route. So we're going to look at position and we're going to analyze it. How do we know that guy's not an operator or literal? Go ahead.
Gotta have like the mechanism to detect, or like the allowable syntax for identifiers. Like most of the C-based languages, like you can't have a number at the beginning of the identifier. Then you have like the apostrophes to denote a char.
So somewhere we need to have the language definition for what are operators. What are the legal symbols in our language? So as far as we can tell by this example here, the legal symbols are the operators equal, plus, times, is that it? Yep. Equal, plus, and times are the legal operators. And we can maybe assume it's all the math operators, but at the very least we know that's the case. Our language also accepts literals, because we see a 60, and it accepts identifiers, variable names. Okay, so we just read in this token position. Is that guy one of, equal, plus, or multiply? It's not. So we check it against our operator, our possible operators. It's none of those. Now we check it against our literal. And seems like literals are, hi, I start with a number.
Yeah.
That's what makes a literal in our simple language here. Okay? Not one of those. So if it's not either of those, it must be an identifier. Right? So I'm going to take this identifier. Well, I'm going to take this token. I'm going to add it to my symbol list. Now, I need to be careful because in our simple little example here, I have not used any variable name more than once. Does that make sense? If I had position represented another time in here, it would be ID1 and it would be ID1 again someplace else. Both of them being pointers to the same place in the symbol table. So I need to get position added to my symbol table. So the first thing I need to do is it already in there? Do I have a variable in there? And we're not even going to talk about scope at this point. We're keeping this simple. Okay, if it's not already in there, we're going to add it. Go ahead.
This is also kind of down the road, but what if we had like overload positions, like one being a double, one being a float, or
Well, that still goes down with scope,
okay.
right? I mean, because you might have position being referenced from two different scopes, although you could never have that. You could never reference position without in an object-oriented language without saying this dot. You could have this dot position being a double and position being an int.
Okay.
You could have that. But you couldn't have position being a double and an int in the same scope.
Hmm.
You know,
Yeah.
one of them's you've either defined it twice and that's an error, okay, or one of them overloaded the other one, shadows the more global variable. All right, so we're going to add position to our symbol table. Then we're going to move on and start reading another token. We read in our next token. We see this guy's an operator. Do we need to add him to any table? Nope. So just wrap him in our little token syntax. Read in the next guy. He is the identifier. Add him to the symbol table. Wrap him in our token syntax. Wrap him. Add him. Wrap him. Wrap him. Wrap them. Okay, so what we're going to do next class, after we talk about the compilers a little bit, when you guys research, is we are going to write this program.
Really get into this quick.
Okay? And then for homework,
More home.
well, I mean, no, the next class, I'm just telling you that sometime soon you're going to be writing this. But like Joey said, it's trivial.
I already did it.
All right. Questions, comments, concerns, bribes. Yep.
You said a string has no white space.
A stream ignores white space.
Okay, but it's still there.
It can be there because it's ignored.
So when we actually take it up there, it will be what space.
Yeah. If you see a space, just skip it.
Well, no, like, why would you have to take it and stop right there? Because it has that white space.
Well, we're going to actually treat it as a character stream, so we're going to read stuff in one character at a time. We're not going to use any of like the tokenizers or anything to split.
Okay.
Well, no, I know, so yeah, we'll take it all the way until 10, but how do we know when to stop? Will it be there in white space?
Yeah, as soon as we hit a white space.
That's what I was thinking.
Yep.
Program that they're writing to the game.
I don't like Wednesdays and Fridays.
We're gonna use Sprint this in class.
Any days.
Probably Java.
Look at how they write.
Yeah.